Chapter 4 is about non-parametric tests. So you have done examples where you used the normal distribution to test the mean of a population, even in cases where the underlying distribution is not known to be normal, but we've used the central limit theorem to assume that they are normal. But this is only if a sample size is large enough. So if the sample is small and the underlying distribution cannot be assumed to be normal, then we can't use a normal distribution, so we need to use a non-parametric test. Okay, the parameters are, say, the mean and the variance, or lambda in a Poisson, or p in a binomial. Okay, so a non-parametric test means that it does not depend on a particular distribution. There is a nice flowchart explaining what we do. So if a sample is large enough, then we can use the normal distribution. Okay, if a distribution is normal, then we can use a normal distribution if we know the variance. If we don't know the variance, then we need to use a non-parametric test again. Okay, so these are the two examples where we use a non-parametric test. If the sample is not large or normal, or if the sample is not large and it's normal, but we don't know the variance. Okay, the simplest non-parametric test is to look at how many of data items lie above or below the median value. So this is called a sign test or a single sample sign test, because there are multiple versions of a sign test. So if the median value in the null hypothesis is correct, then there is a probability of half of being above or below the median. Yeah, so that means that you can use the binomial distribution to find a p-value for the result of the sample. And a reminder, just like normal hypothesis tests, that the p-value is the probability of the given result or more extreme. This hopefully makes more sense when I do an example. So just a couple of quick points. If the test is two-tailed, then you have to halve the significance level and only check one side of the distribution. A normal test involves testing for the mean, whereas this test refers to the median. But you will recall that if the data is symmetrically distributed, as is required for this test, then the median is always equal to the mean. So the only assumption required for this test is that the data is symmetrically distributed about the median. So our first example here. So over a long period of time, Mike has found that the median of the time he takes to drive to work is 46 minutes. After a new road layout is introduced, Mike suspects that his journey time has increased. His times, the journey over the next 14 working days, are as follows. Use a sign test to determine at the 5% level whether there is evidence to suggest that the median journey time has increased. So first things first, as always, set up our hypothesis. So H0, the median journey time is still 46 minutes. And H1, as we're looking at see if it's increased, the median journey time is greater than 46 minutes. Okay, if we say X is the number of journeys that take longer than 46 minutes, then I can say that X is binomially distributed with n14 and p 0.5. Why is this the case? Because if the median is 46, then I expect half to be above and half to be below. Okay, let's have a look how many are above the 46. So 53, so 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 values are bigger than 46. So what this means is I'm going to find the probability that X is bigger than or equal to 9. Yeah, because I've got 9 values, I'm looking at the top end, so I'll do probably X is bigger than or equal to 9. So that's 1 minus probably X is less than or equal to 8. So if I do that in my calculator, so menu 7 down to 1 there. Very well. So X is 8, N is 14, P is 0.5. and I'm doing 1 minus the answer, and I get 0.212. Okay, this is bigger than 0.05, which is my significance level, so that means I'm accepting H0. So just like an old-fashioned hypothesis test. And then, nice summary statement, there is insufficient evidence to suggest the median journey time has increased. Okay, reasonably straightforward. I'm going to do one more example just to make sure. So our second example here, a sprinter has for a long time held a median sprint time of 10.21 seconds. After a new training regime, he runs 600 meter races in these times. He believes he has lowered his median time for the 100 meter. Statement: null and alternative hypothesis for the test, and use a sign test to test the hypothesis at the 5% level and state the conclusion. So in the previous example, we wrote out the hypothesis in words. You can also write it out in terms of the median m. So if I let m be the median time for sprinter to run 100 meters, then my H0 can be m equals 10.21, and then my H1 can be m is less than 10.21. Okay, then part 2, actually do the test. So how many values will I have less than 10.21? So 1, 2, 3, 4, 5. So I've got 5 values, but I'll make a note of that in a bit. So we first need to let x be the number of times the sprinter races under 10.21 seconds. Then that means I can distribute this as x is binomially distributed with n equals 6 and p equals 0.5. I've got 5 values less than 10.21. So that means I'm doing probability x bigger than or equal to 5 still, because I've got 5 values and I go bigger than. So this equals 1 minus probability x is less than or equal to 4, which is 1 minus 0.891, which equals 0.109. Now, some of you amongst will just say, well, why don't you do probability x is less than or equal to 1? Because that's going to be the same as probability x bigger than or equal to 5, because binomial with probability 0.5 is symmetrical. Again, it's the same. This is exactly the same as the probability of x is less than or equal to 1. So you can do it whichever way around you want to. But for now, I'm just writing out in full so that we get the ideas across before we start making some shortcuts. And this is bigger than 0.05, so we accept H0. So there is insufficient evidence to suggest that the sprinters' times have improved. Now, this may be counterintuitive because 5 out of 6 have improved, but because the sample size is so small, we cannot say it with enough conviction at the 5% level. So the sign test is a bit basic because it does not take into account how far above or below the median each data item is. Okay, just says whether it is or isn't. To get a bit more involved, we use the Wilcoxon signed rank test, and this is better because it does take into account that distance. In this test, the absolute value of the distance from the median of each data item is calculated, and these distances are then ranked. The ranks of all the items above the hypothesized median are added up, and we call this W+, and the ranks for all the items below the hypothesized median are W-. then what do we do with these values? So the test stat t is the smaller of w plus and w minus, and then we take critical values from the formula books. So I'm going to slightly alter the examples previous to make them a Wilcoxon test. A quick point about understanding the test though is in most of the hypothesis testing you've done so far, you've rejected the null hypothesis if the test stat is numerically larger than the critical value. However, in this test, we reject the null hypothesis if the test stat is less than or equal to the critical value. This is because if the test stat, either w plus or w minus, is small, then there must be a large difference between w plus and w minus. So that indicates that the supposed median is not in fact the centre of the data. So that is why this is the opposite way around to our normal critical value hypothesis test.
Okay then, let's start using some colour. So I'm going to go back to the two previous examples and do a Wilcoxon signed rank test instead of the normal sign test. So it starts off the same, H0 and H1 are still the same, median journey time is 46, and H1's median journey time is greater than 46. Now what I need to do is I have my times, I've tabulated them instead, and what I need to do is, because the median is 46, I need to do these times, take away 46, and take the absolute value of them. Okay, so that will give me 7, 5, 4, 2, 3, 1, 5, 4, 3, 12, 1, 8, 5 and 1. And at this point it's also worth noting which ones give you a negative value as well. So the ones which give me a negative value are 42 and 44 and 45 and 43 and 41. So those give me the negative values. It's important to make note which ones are negative, because when we do the W minus, W plus, we need to distinguish between positive and negative. Okay, then we need to rank stuff. Okay, we've got 3 values with 1, so we need to rank those. So because they're 1, 2 and 3, we rank them all as the middle values, so we rank them all as 2. So that means this is going to be a rank 2, and rank 2 as well. Okay. Similarly, I've got 2 which are 5, so I'm going to rank those the same way. So I've got 1, 2 and 3, so my next value of 2 is going to be rank 4. Then the 2 values of 3, so I've got 3 and I've got 3, so they should be rank 5 and should be rank 6. That means they're going to be the middle value, so that's going to be a rank of 5.5. So that's 5.5 and 5.5 there. Okay, then the next value is going to be a rank 7. So that's going to be my 4s, but I've got 2 4s, so that's going to be 7 and 8. So that's going to be rank 7.5 for those two. So 7.5, 7.5. And I've got 3 5s, so they would be 9, 10 and 11, so they are all ranked 10. 10, 10 and 10. Now we'll just do it as normal, so our next value is the 7 at the top, so that gives me a rank of 12. Then I've got the 8, so that's rank of 13, and rank 12, rank 14. Okay, so if there's any tied ranks, we just take the middle value. Okay, so now we need to work out the total rank for each of them. So if I've got W plus, okay, that is 12 plus 10 plus 5.5 plus 10 plus 7.5 plus 14 plus 2 plus 13 plus 2. Okay, so those are our positive values. So that gives me 76. And for W minus, I'm adding up the minus value, so 7.5 plus 4 plus 2 plus 5.5 plus 10, that gives me 29. Okay, there is a quick way of checking that you've done this correctly, and that is by using the formula for the sum of the natural numbers. Okay, that formula is n plus 1 over 2. So as n is 14, so that means 14 times 15 over 2, which is equal to 105. That means that these two values should add together to 105. So if I do 76 plus 29, I get 105, so I've done it correctly. Okay, so this is just a quick check you can do to make sure that you've done your rankings correctly. They should add up to the sum of the natural numbers. Yeah, because all I'm doing is adding up the numbers of 1 to 14, so it should work. Right, then I need to work out my test statistic. So my test statistic is the lower value of W plus and W minus. So my test statistic T is the same as W minus, so that equals 29. Okay. Then I need to find out my critical value. So for my critical value, I need to use the table. So this is the one for the Wilcoxon signed rank test. I'm doing it at the 5% level where n equals 14. So n equals 14, 5% level. That means my critical value is 25. Yep. So at 5% level with n equals to 14, critical value is equal to 25. Now, because t is bigger than 25, that means I am accepting h0. Okay? And now I need a nice summative statement. There is insufficient evidence to suggest that the median journey time has increased. Okay, I'm going to do the same for our second example in the sign test. So again, the same question about the sprinter. We've already done the first two parts, now we're just doing the third part. So I've tabulated the times again, and I need to do the times, take away the median, and I want the absolute value. So this is 0.02, 0.03, 0.04, 0.03, 0.04, and 0.07. And we need to make note of which ones are the negative values. So I have minus, 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 and minus. Okay, then I need to rank them. So this is going to be rank 1. Then I've got 2 of rank 0.03, so that means they're both going to be rank 2.5. Then I've got 2 of rank 0.04, so that means they're going to be in between 4 and 5, so 4.5. And the final rank is going to be 6. Okay. Then I need to work out W plus and W minus. So W plus is just this value, so 2.5. W minus is the other values added together, so 1 plus 4.5 plus 2.5, etc. So that gives me 18.5. Check that we've done it correctly, so we do n plus 1 over 2. So I've got 6 values here, so I need to do 6 times 7 over 2, which equals 21, and that is equal to 18.5 plus 2.5, so I've done it correctly. Okay, my test statistic T is equal to the smaller of these two, so that equals W plus in this case, so that's 2.5. Then I need to work out my critical value. So this is a one-tail test at 5% with n equals 6. So at 5%, n equals 6, my critical value from my table. So 5%, n equals 6. My critical value is equal to 2. So T is bigger than my critical value. So that means I'm accepting H0, because remember it's the opposite way around of our normal critical value tests. And a nice summative statement. There is sufficient evidence. Sorry, insufficient. Well, there's insufficient evidence to suggest that the sprinter has improved their time. Okay, moving on.
So most data you use for hypothesis testing is paired, but you can get unpaired samples as well. So most of the time, the paired data is, say you've got say one value of x and it continues over time, and you're comparing it over time, or you're comparing two similar sets of data. So if paired samples can be used, this is all good. We have tests for that, but if it's unpaired, we can still do some experiments with them. Okay, so here is a standard situation of paired data. So as you have two weights for each baby, you have a set of data birth weights for one set of babies, another set of data for weights for a different group of babies, and then we can compare them. Obviously, this would be quite useful to do in some fields. So for a paired test, then we can use either the sign test or the Wilcoxon sign rank test, often called the Wilcoxon paired sample test for obvious reasons. And to do this, we apply the test to the differences between the pairs. If you're asked for any assumptions in an exam, then you must refer to the differences. Okay. So when using the Wilcoxon paired sample test, you are assuming that the differences are symmetrically distributed about the median value of the difference. This is usually 0, but it can be different. But if you can't work it out, just go with 0. This is very similar to the assumption for a normal sign test, so it shouldn't be that hard to recall.
So our first example, a psychologist claims that the number of repeat offenders will decrease if first-time offenders complete a particular rehabilitation course. You randomly select 10 prisons and record the number of repeat offenders during a 2-year period. Then, after first-time offenders complete the course, you record the number of repeat offenders at each prison for another 2-year period. The results are shown in the following table. At the 0.05 significance level, can you support the psychologist's claim? So here is our table. So the first thing we need to state is our H0, but before we do that, we need to say what MD is. Okay, so MD is the median of differences. Okay, and our H0 is MD equals 0, so the median of differences is 0, and our H1, our median of differences is bigger than 0. Okay, the reason it's going to be bigger than 0 is because I'm doing before, take away, after. So if I do before, take away, after, I want my median differences to be bigger than 0. Yeah, I want there to be, I want it to be a positive answer because that means they've improved. Okay, so if I do the differences here, so 1, 2, I'm doing 1, take away 2 to look at the effects. So that means I've got 2, 12, minus 7, 14, 9, 24, 15, 18, 16, and 19. So because these median differences, there should be some above and some below 0. So I would have x is binomially distributed with 10 and 0.5. I've only got 1, which is less than 0. So I could do probability x bigger than or equal to 9, but that's the same as probability x less than or equal to 1, as we said in the previous chapter. So I'm going to do probability x less than or equal to 1, which equals 0.0107, which is less than 0.05. Therefore, I reject H0, and there is our final statement, so sufficient evidence to suggest that the psychologist's claiming is correct. Okay, so that's a easy sign test example with paired data. The only difference here is we have MD instead of our normal median, and we say our median difference is equal to 0. Okay. On to our second example. So the individuals in the list below had their blood pressure checked in the morning and again at night. use the table to perform a Wilcoxon signed rank test with 5% significance to determine whether blood pressure is lower at night than in the morning. So here is our table of data. What we need to work out is we need to work out the differences. So the differences I'm going to do, again, do 1 take away 2. So we add the differences in here. And so that's going to give me 10.2, 8 minus 1.9, 6.7, 6.8, and 4.2. And then I need to rank the absolute values of D. So that means the first one is going to be the 1.9. Then the second one is the 4.2. Then the 6.7, the 6.8, 8 and 7.2. Where this one is the negative value. Okay. Right, from there I can start writing my hypothesis. So if we let MD be the median difference between morning and evening, blood pressure, then my H0 is going to be MD equals 0, then my H1 is going to be MD is less than 0 because I'm looking for it to decrease. So I'm hoping that the blood pressure is lower at night than it is in the morning. So here I need to work out W plus and W minus as I usually would do. So W plus is going to be the 6 plus the 5 plus the 3 plus the 4 plus the 2. So that gives me 20, and my W minus is going to just be equal to the 1. Yeah, we can still do our normal check, so check it's correct. So n plus 1 over 2. So that is 6 times 7 over 2, which is 21. These two add up to 21, so it's all good. Okay, our test statistic T is thus equal to W minus, which equals 1. Then I need to work out my critical value. So at 5% level with n equals to 6, I need to get my table of values here. So 5% level, n equals 6, I've got 2. So my critical value equals 2. So as t is less than 2, that means I am rejecting H0. Then I need my summative statement at the end. There is sufficient evidence to suggest that blood pressure is lower at night. Okay, one more example style question just to make sure. So the last example, a security firm believes that good short-term visual memory is an important attribute for its officers, and a psychologist is investigating whether this can be improved by a special coaching program as part of the initial training of new recruits. Each of a random sample of 12 new recruits takes a standard short-term visual memory test before and after the coaching program. The results are as follows. Use an appropriate Wilcoxon procedure to test whether short-term visual memory has been improved at a 5% level of significance. So I need to find my differences. So differences, I'm going to go D, and I'm going to do the after takeaway before, just to show that it can be worked out the other way. So if I'm doing that, then, and I need to rank that as well. So I've got my modulus D. So if I do 52 take away 58, sorry, 58 take away 52, so I get 6. The reason I'm doing after take away before is I want it to increase. Yeah, so that's 6, and then 11, then 22, and then 5, but it's a minus, then 1, also a minus, then 4, 28, 7, oh sorry, 2, the next one is 7, 2, 7, 3, 9, and 8. With the ones being negative being the 5, the 1, and the 2. Okay, now I need to rank. So ranking these, just for sake of time I've already done it, so 6, 10, 11, 5, 1, 4, 12, 2, 7, 3, 9, 8. So my H0, I'm going to write in words instead of using MD as well, just to show it can be done in words. So the average difference is 0, and H1 the average difference is greater than 0, because again I'm looking for an increase. Okay, so W plus is going to be equal to the 6 plus the 10 plus the 11, etc. So that equals to 70. W minus is going to be the 5 plus the 1 plus the 2. So that's equal to 8. Check I've done it correctly. So n plus 1 over 2. So 12 times 13 over 2 equals 78. 70 plus 8. That works, I've done that correctly. So test statistic T is going to be equal to W minus, which equals 8. This is a one-tailed test at the 5% level with n equal to 12. Therefore my critical value from my table, 5% level, n equals 12, it gives me 17 as my critical value. So my T is less than my critical value. That means I'm rejecting H0. Summative statement, there is sufficient evidence to suggest that the scores have increased. Okay, now we move on to unpaired tests.
Now, if I have an unpaired test, we can use a Wilcoxon rank sum test, and this involves ranking all the data from both samples. Okay, this is the method of doing so. It is in your formula book, so it isn't too much to worry about. But we have two samples which sizes m and n, where m is less than or equal to n. Then we rank all the values from both samples in order of increase in size, the lowest value getting a rank of 1. Rm is the sum of the ranks of the items in a sample of size m. W is the small of Rm and m times by m plus n plus 1 minus Rm. We use the table of critical values of W to conduct the test. Okay? That's not too tricky going through it, as long as we set it out in each step. And again, this is in your formula book.
So on to an unpaired example. So the weekly earnings of a sample of 8 men in full-time employment and a sample of 10 women in full-time employment are shown below. Carry out a Wilcoxon rank sum test at a 5% significance level to investigate whether there is evidence that men are earning more than women. So start with our hypotheses. So H0, there is no difference between the median weekly earnings of men and women, and our H1 is the weekly median earnings of men is higher than women. Okay, so we need to rank these values. Okay, so I'm actually going to write over the question in pen, which is madness. So I need to rank all of them. Okay, so not just in the men or in the women, I need to rank all of them. So I need to rank them 1 to 18, where 1 is the smallest. So my first one is this 200.48. Yeah, the second one is going to be 201. Yep, third one there, fourth one there, then my fifth one going up to the men, sixth back down to the ladies, and seventh there, eighth is the 446, 9, 4, 5, 7, 10 will be the 448 there, then we go to the 11 and the 12 and the 13th is the 571, the 14th is here, then we got 15th, 16th, 17th and 18th. Okay, so we've got all those values ranked now. So that means that the total rank for men is the 8 plus the 5 plus the 12, etc. So that is equal to 100, and the total rank for women is the 1 plus the 7 plus the 13, etc. That gives me 71. Okay. We know that the M is the smaller sample, so in this case the M is the men. So that means that my RM is equal to 100. And I just need to check that I've done this correctly. So again, using n plus 1 over 2, I've got 18 values, so I need to do 18 times by 19 over 2, which equals 171 as required. So we've all done that good. Okay. So I've got RM equals 100. I also need to work out M plus N plus 1. Yeah, because M is equal to 8, N is equal to 10. So this is equal to 8 times, minus RM. Ooh. So this is equal to 8 times by 19 minus 100. So that equals 52. So my test statistic is the smaller of these two, which is called W. So W is equal to 52. Okay. Then we need to work out our significance level, our critical value. So significance level is 5%, and we're doing M equals 8, N equals 10. So we get our table of values from our formula book there. So M equals 8, N equals 10, and I'm doing it at 0.05, so my value is 56. Therefore, critical value equals 56, and W is less than critical value, therefore I am rejecting H0. Yeah. And summative statement, there is sufficient evidence to suggest that the weekly earnings for men are higher than women. Okay, I'm going to do another example just to make sure. So an exam style question: a company operates 2 call centres for telephone calls from the public. Managers are investigating the service standards of the 2 centres. An experienced manager contacts 6 callers to the first centre and 7 callers to the second. Each caller is interviewed in depth over the telephone and asked to arrive at an overall satisfaction score combining several aspects of the service. These satisfaction scores are regarded as random samples from corresponding underlying populations for the two centres and are as follows. High values are a good service. Using an appropriate non-parametric test at the 10% level of significance to examine whether there are, on the whole, any differences between the satisfaction scores for the two centres. So starting off with our hypotheses. So H0, the median satisfaction score are the same at both centres. And then H1 will be the median satisfaction scores at the two centres differ. Okay, we can work out our critical value right away. So I've got M is equal to 6, N is equal to 7. It's two-tailed at 10%. So if I look at my critical value sheet here, so N equals 7, M equals 6, two-tailed 0.1 gives me a critical value of 29. Okay, now we need to rank these values. So because the top score is good service, it doesn't really matter which way I rank it. So I can rank from smallest to biggest, the smallest. I'm still going to go from smallest to biggest. So 26.7 would be 1. And then 2 would be 28.8. 3 would be 29.4. Etc. I'm just going to fill these in as I've already done it, and to save a bit of time, because I'm assuming you can rank numbers. There we go. So now I just need the total ranks. So RM in this case, so the rank of the smaller value, so 10 plus 9 plus 12 plus 7 plus 13 plus 4, that is equal to 55. Just for completeness and to make sure I've done it correctly, the rank of N is going to be equal to 8 plus 6 plus 3, etc. That equals 36. And to check I've done it correctly, N plus 1 over 2. So I've got 13 values. So 13 times 14 over 2 is equal to 91. 55 plus 36 equals 91. So yeah, we're all good. And M plus N plus 1 minus RM. So that's 6 times by 14 minus 55. So that equals 29. So that means my test statistic W is equal to 29, and because W is equal to my critical value, that is still rejecting H0. Yeah, it has to be bigger than my critical value. Yeah. So there is sufficient evidence to suggest that the median satisfaction scores in each centre differ. Okay, finally on to normal approximations.
On to normal approximations. So in the formula booklet, the table of critical values only goes up to n equals 20 for single sample and m equals 10, n equals 10 for dual samples. That's because for larger samples, you can calculate the critical value by using a normal approximation, using the formula in your formula book. Okay, again, these are not to be proven, you just need to take my word for them. However, as you are approximating a discrete distribution with a continuous one, then we have to use a continuity correction. Okay, so as W plus minus and Rm are integers, but a normal distribution is continuous, we need to cover the interval, which is plus or minus 0.5. So if I have W plus equal to 12, then I have to consider 11.5 to 12.5. Yeah, this makes sense because if I have a normal distribution, I can't have it equal to 12, that equals 0. I need to do it over the interval 11.5 to 12.5. So when calculating the p-value, we choose the end that makes the tail as large as possible. So if W plus or minus or Rm is less than the mean of the normal distribution, then you choose it plus 0.5 and vice versa. I'll show this in a bit more detail with some examples. But we have our formulas for the signed rank and rank sums. So W is normally distributed with these parameters and Rm is normally distributed with these parameters.
So starting off slowly, for a single sample Wilcoxon signed rank test, find the critical value for a one-tailed test at the 5% level with n equals to 50. So we can say that T can be approximated by a normal distribution with mean equal to a quarter times by 50 times 51. Therefore, mu is equal to 637.5, and variance is 1 over 24 times by 50 times by 51 times by 101, which equals 10731.25. Which is the variance there. Okay. But we also need to use a continuity correction here. Okay. So using a continuity correction, we need the integer t such that the probability of t less than or equal to t plus 0.5 is less than or equal to 0.05. Yeah. So we need to use an inverse normal. So using inverse normal. So go and calculate here. So inverse normal. We've got our area is equal to 0.05. Our sigma is equal to the square root of 10731.25. And our mu is equal to 637.5. And we get the value 467.1. But that is what t plus 0.5 is equal to. Yeah, so that t is equal to 467.1. So that means t is equal to that, take away 0.5. So that is equal to 466.6. So that means my critical value is 466. Yeah, because t must be an integer and the probability must be less than 0.05. Yeah, here we've done it equal to 0.05 in our inverse normal. So to get it less than 0.05 will be 466. Yeah, that will guarantee it less than 0.05. 467 gives me bigger than 0.05. Okay, I'm going to do one more example like this just to make sure. So for a Wilcoxon rank sum test, find the critical value for a one-tailed test at the 5% level with m equals 13 and n equals 17. So here I can have w can be approximated by a normal distribution with mean of a times by m, which is 13, times by n plus 1, so 13 plus 17 plus 1 is 31, 201.5, and variance 12 times by 13 times by 17 times by 31, which is 570.92, and again we need to use a continuity correction. So using continuity correction, we need an integer w such that the probability of w less than or equal to w plus 0.5 is less than or equal to 0.05. So again, using an inverse normal, so menu 7 inverse normal, area 0.05, sigma is the square root of 570.92, and mu is equal to 201.5. We get 162.19. So that means small w, this will be capital W here. So menu 1, answer take away 0.5 gives me 161.69, etc. So therefore my critical value is going to be equal to 161, because it needs to round out. Okay, I'll do one last exam style question and then we're done. So a Wilcoxon rank sum test is to be performed on 2 unpaired samples taken from populations P and Q. Hypotheses to be tested are as follows. The data from the 2 samples are ranked. P has size 20 and the sum of the ranks RP equals 572. Q has size 25 and RQ equals 463. Find the test stat, use a normal approximation to calculate the critical value for this test, and complete the hypothesis test. So for the first part here, I've got m equals to 20 and n equals to 25. I've got rm is equal to 572 because it's my smaller value, and n plus 1 minus rm is equal to 348 if I put the values in. So therefore test statistic is the smaller of these two, so 348. On to the second question. Use a normal approximation to calculate the critical value for this test. So here I need to work out the mean and the variance from my calculation. So I'm assuming you can do that by now. So n is 460 and 1916.67. And we need an integer w such that probability of w less than or equal to, I'll put it over here, such that probability of w less than or equal to w plus 0.5 is less than 0.025, because this is a two-tailed test. Yeah, it just says populations are different. So using an inverse normal, that gives us w is equal to 373.7. I'm assuming you can do an inverse normal and take away 0.5 by now. Yeah, so therefore critical value is equal to 373. Then the last part, complete the hypothesis test. So the test statistic is less than my critical value. So that means I am rejecting H0. Summative statement, there is sufficient evidence to suggest that the medians of the 2 populations differ. All done.